So we're coming to the end of this exceptional semester. I know it's not been easy for all of us to have the sudden transition to online distance learning, but I'm very glad I got to share this semester with you, and I'm very proud of all of you who have tried hard, tried their best to stay motivated and to continue learning despite the difficult and strange circumstances. And I hope you're all getting ready, preparing well for our final exam that's going to be on Wednesday morning. So now I want to use this video to give you a brief overview of one of the most fascinating and beautiful subjects in mathematics, and that's related to one of the last topics that we studied in this course. So if we take a look again at the these familiar three Taylor series, the Taylor series expansion of e to the x, or the Maclaurin series of e to the x, which is 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4 over 4 factorial, plus x to the 5 over 5 factorial, plus so on. Cosine x is, we know that it's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus so on. And sine x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus so on. So as some of you have already probably have seen that cosine x looks like and sine x look like the power series expansion, Taylor series expansion look like coming as part of this Taylor series expansion of e to the x. In particular, cosine x looks like the even part of the power series expansion of e to the x, and sine x look like the odd part, the part with odd powers of x, but with this strange alternating sign of coming along. So are they in fact related? Are these three series related? Are these three functions related? It turns out, is the answer yes or no? It turns out that the answer is yes, but to understand that, we need to understand something about complex numbers, complex variables, and functions of complex variables. So we start with the following, and we know that the equation x squared plus 1 equals 0 has no real solution because we cannot take the square root of negative 1. The square root of negative 1 is not, there's no real number whose product with itself gives you negative 1. But if we decide that we want to solve this equation, we can introduce a new number, which we usually denote by I. Define I to be the square root of negative 1. This I is called the imaginary unit. And if I equals square root of negative 1, then I squared equals to negative 1. And then we can rewrite x squared plus 1 as x squared minus I squared. Factor x squared minus I squared as a difference of two squares, as x minus I times x plus I, and from this we get that x squared plus 1 equals 0 has two solutions, x equals positive I and x equals negative I. Are we justified? Can we just introduce a new number, call it to be square root of negative 1 and say that okay, we solved our problem? Turns out that yes, we are justified. It took some convincing, like in the beginning mathematicians did not accept that square root of negative 1 exists, or we can call that, and that's why the name imaginary comes from the fact that ki is an imaginary number, but turns out that there is a very satisfying theory of what's called complex numbers. We can extend the real numbers or the real number system into the complex number system. And the complex numbers we can take them as these expressions, a plus bi, of the form a plus bi, where a and b are real numbers, and I is the imaginary unit whose square is equal to negative 1. And now these new numbers there, you can add them, subtract them, multiply them, and divide them by the same rules like of algebra that you use for real numbers. And we can, whenever it's possible, whenever it's needed, you can simplify powers of I as follows, using that I squared equals negative 1. So I cubed, which is, we can write it as I squared times I, and I squared is negative 1. So you get negative 1 times I, or negative I. I to the 4, you can write it as I squared times I squared. So negative 1 times negative 1, which is positive 1. I to the 5 is I to the 4 times I to the 4 we just said is I. And so I to the 5 is just 1 times I, or it's I. And we can just add and subtract and divide and multiply and and I don't want to spend time on this, but also I want to tell you that we can also represent complex numbers in on the Cartesian plane. So we take the x-axis to represent the real axis, represent the real numbers, and the y-axis is the imaginary axis, represents multiples of I. And then now any point in the now we call that plane the complex plane. Any point in the complex plane represent a complex number, a plus bi, and any number is represented by a point on the complex plane. And turns out that addition and subtraction of complex numbers have very nice geometric representation, because we can represent every now point on the plane, on the complex plane by a vector, its position vector from 0. And then addition of two complex number is addition of two vectors, and multiplication of two complex number is very interesting. Becomes a rotation of one vector by the angle of another, and scaling of magnitudes with the scaling of magnitudes. So now with the complex number, we can not only solve the equation x squared plus 1 equals I, but we can solve any quadratic equation. Because, for example, if you take the quadratic equation x squared minus 6x plus 13 equals 0, and we apply the famous quadratic formula, we get x equals 6 plus or minus square root of negative 6 squared, so 36, minus 4 times 1 times 13, so minus 52 under the square root over 2. Square root of 36 minus 52 is square root of negative 16, so square root of negative number. There is no real solutions for this equation, but we can write square root of negative 16. We can take the square root of 16 as 4 and rewrite this as x equals 6 plus or minus 4 times square root of negative 1 over 2. Square root of negative 1 is I, so we get 6 plus or minus 4i over 2, which simplifies to 3 plus or minus 2i. So this equation, which didn't have real solutions, had two complex solutions, two complex roots, x equals 3 plus 2i and x equals 3 minus 2i. And actually much more is true. If we take any polynomial equation with any degree, so if you take any polynomial with any degree, then if this polynomial will have exactly n roots in the complex numbers. Some of these roots might be repeated or might be equal, but it will have, any polynomial equation will have exactly n solutions. And moreover, even if you allow these coefficients of the polynomial to be complex numbers, not just real numbers, this theorem or this result is true, that every polynomial equation, even with complex coefficients, have exactly n complex roots. This theorem is called the fundamental theorem of algebra. If you pursue more math or take more math courses, you will probably see the proof of this theorem. It could be proved in different ways, and it's one of the most remarkable results in math. So now let's go back to our power series. So what about power series? What about with complex numbers? So what if you allow x now, replace x by a complex variable, usually denoted by z. Z represents complex numbers, and can we talk about complex power series? Turns out yes, there is a very satisfying theory for complex power series, and actually you will understand the real power series in a deeper way when you study complex power series. And like maybe it will sound strange when I see it now, but if you have a function of complex variables, and then if this function is differentiable in a region R in the complex plane, then it has to be infinitely differentiable. It has to have derivatives of all orders. If it have just the first derivative, it has to have derivatives of all orders. And moreover, if you take any point A inside this region R and you form the Taylor series expansion of your function in around the point A or in powers z minus a, then this Taylor series will converge to the function in any circle. For complex numbers now we talk about circles instead of intervals of convergence, in any circle centered at A and that lies inside the region R. So and from these results we will get that these power series expansions for e to the x, for cos x, for sin x are still valid. These four are still work when x are still converge when x is replaced by a real variable z, and they will converge everywhere for all complex variables. So in particular, let's now we can replace x here by ix, I our imaginary unit, and say e to the ix equals to 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4 over 4 factorial plus ix to the 5 over 5 factorial. And now we simplify using these simplifications for the integer powers of I. So we get 1 plus ix, I squared is negative 1. So to get negative, we get the negative sign, negative x squared over 2 factorial. I cubed is, we said I cubed is negative I. We get negative I x cubed over 3 factorial. I to the 4, we said that this is 1. So plus x to the 4 over 4 factorial. I to the 5 is I. So we get back I times x to the 5 over 5 factorial minus and so on. And now convergence, we have the notion of absolute convergence also for complex power series, and when a series is absolutely convergent, you can rearrange the terms of the series without changing the sum. So we rearrange the terms. We take the even terms, the terms with even powers together. We get 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus so on. And now we notice that all the odd powers are multiplied by I, all the odd powers of x. So we can factor out the I, and we write the odd powers of x together, forming the power series x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus and so on. But this first power series here is just the power series of cosine x. And the second power series here that's multiplied by I is the power series expansion of sine x. So from this last equation here we get what's called Euler's formula. Euler's remarkable formula tells us that e to the ix equals cosine x plus I sine x. So when we first introduced exponential and trigonometric functions in calculus, or even before in high school, we didn't expect that there could be a relation between the exponential function and the trigonometric functions. But it turns out that there is a very intimate relation between the trigonometric functions and exponential functions, and it's expressed by this Euler's fantastic formula. Now if we take this Euler's formula and we replace x by negative x, we get e to the negative ix equals to cos of negative x is equal to cos x, because cosine is an even function, so we get equals to cos x, and sine of negative x equals to negative sine x, because sine is an even function, is an odd function. So you get e to the negative ix equals cos x minus I sine x. Now adding these two equations together and dividing by 2, it gives you this expression for cosine x as e to the ix plus e to the negative ix over 2. And subtracting the second equation from the first equation and dividing by 2 again, you get the formula dividing by 2I in this case. You get that sine x equals to e to the ix minus e to the negative ix over 2I. So these two formulas for cosine x and sine x are useful in advanced math and in physics and also some engineering. And lastly, if we take Euler's formula and we replace x by pi everywhere in this formula, we get e to the pi I equals cosine pi plus I sine pi. Cosine pi is negative 1, sine pi is 0, so we get e to the pi I equals to negative 1. So we get this remarkable relation between the three most famous constants in math, e, pi, and I. And so this relation here is saying that e to the pi I equals negative 1. So e to the pi I is the negative square root of 1. And this is more generally, this is a special case of a more general result that says that e to the 2 pi I over n is an nth root of, always an nth root of 1. So complex numbers and theory of complex variables, which is called complex analysis, is one of the most beautiful and rewarding subjects in mathematics. If you get to the chance to study it, I highly recommend it. And besides, like, complex numbers and functions of complex variables have a very deep and very real applications in physics and engineering, especially electrical engineering. So if you're pursuing studies in math, physics, or engineering, you probably will encounter complex numbers and their functions at some point.